Welcome everyone to my Living Lab Lecture series talk. My name is Benjamin Uhrich and I'm happy to present you today how we can use physics-informed machine learning to optimize 3D printing processes. The objective of the talk is the development of physics-informed neural networks for intelligent real-time modeling and simulation of temperature processes in additive manufacturing. For that purpose, I will show you how we can efficiently analyze real experimental measurement data from Siemens. I will compare different computational approaches with each other and show the advantages of the optimization of 3D printing processes with such a digital twin. And of course, I recommend to apply these methods during 3D printing. I divided my talk into 6 parts. So first I will give an overview of general heat transfer mechanisms. The second part is about data generation and material properties. After that, I will give an introduction to physics-informed machine learning approaches. As I said on the slide before, there will be a comparison of the resulting heat models. This will be the first part of my talk. There are simplifying assumptions in the models here, but the real world is much more complex. So in the second part, I will optimize the heat models, and at the end there will be a summary. Let's start with the question, what is a digital twin? There are many different definitions of digital twins. From my point of view, a digital twin is, at best, a comprehensive digital representation of all physical processes within a complex industrial system. Which components are necessary for this, I have shown in the right figure. So, a digital twin is required data-driven physics-informed machine learning models. Also, common mathematical models are required. We need also data input from multiple sources like sensor data and simulations. High volume data streaming in real time is required. We need multiple subsystems, length and time scales, and at the end, also intelligent analysis and visualization are needed. So with the help of all these parts, a digital twin enables monitoring, diagnostics and predictions of a complex system. The aim is to improve the performance, reliability and availability of complex industrial plants and to make maintenance more cost efficient in order to optimize production processes. In the next few minutes, I will try to show you in partial aspects how to develop such digital twin for a subsystem of 3D printing. So first, we need to understand what is happening and where issues can arise. I have brought you a video today here, so I'm not sure to what extent you are familiar with 3D printing processes. So as you can see, metal powder is applied and melted or fused with the aid of a laser. In this way, a component is created layer by layer, and it's possible to produce complex geometries individually. These melting processes result in repetitive heating and cooling cycles and thus represent one of the main factors influencing component quality. For example, heat accumulations can lead to deformation of the component, and to avoid this, we need to understand the temperature processes better. Basically, there are three heat transfer mechanisms. So first, there is heat conduction. Here, heat is transported through direct physical contact. As you all know, metal is a very good heat conductor. There's also convection. Here, heat is transmitted by currents in a fluid like liquid or gas. During melting, metal changes its state of aggregation from solid to liquid. So this heat transfer mechanism is also applied in 3D printing. And at the end, there's radiation. This is a heat transfer mechanism through electromagnetic waves without physical contact between objects. Radiation is also used in 3D printing, and another good example for radiation are thermal imaging cameras. These are required for sensor data generation. So Siemens uses two different 3D printing machines with two different platform spaces. Both machines are equipped with thermal imaging cameras. The cameras has a resolution of 382 by 288 pixels and maximum frame rates of 200 Hz. Materials used are IC360L, it's a stainless steel, and Inconel 718, it's a nickel-based alloy. On the right side, you can see printed prototypes in form of upside-down pyramids from Siemens. A thermal imaging camera is not able to measure temperatures directly from the surface. Instead, the thermal radiation from this surface is collected. This thermal radiation is then correlated to a temperature. Anybody above 0 Kelvin emits radiation. In the diagram, this thermal radiation is shown as functions of wavelength for a black body, so-called Plancks Law. Perfect black bodies are an idealized thermal radiation source. Thermal imaging cameras from Siemens range from 7 to 14 micrometer wavelength. But this range applies only to perfect black bodies. Our metal surfaces are not perfect black bodies, so the emissivity of metal surfaces must be taken into account. This is not so trivial. An estimated factor of 0.4 is chosen for these emissivities. It is important to mention here that exactly for this reason, the measured temperature values are not numerical exact temperature values, but a measured temperature increase corresponds just as well to a real temperature increase. We know that for sure. And it's precisely to predict these temperature increase that physics-informed machine learning approach offer great potential. It is possible to incorporate these descriptions into deep neural networks and thus increase the prediction accuracy and reduce the required amount of sensor data. The resulting hybrid models can thus combine physical interpretability and extrapolation capacity of partial differential equations with data-driven machine learning capabilities of deep neural networks. There are several ways to develop such temperature models. The first model I would like to present here. The temperature process is described by a very general partial differential equation, which can be used to formulate a variety of real natural phenomena. In the next one, a deep neural network, a fully connected deep neural network, is used as an initial function and trained in such a way that it can approximate the temperature process as well as possible. Then another deep neural network is trained to learn the function theta from the approximated temperature field, its derivatives, and the heat source in such a way as to decipher the physical laws of heat transfer in 3D printing. The goal of the optimization of both networks is shown here in the loss functions, which has to be minimized. So there are two main restrictions for the learning process. So first, the approximated temperature function should be as close as possible to the temperature observations, and simultaneously the found partial differential equation has to be satisfied. This is a simplified model in which only the temperature distribution by heat conduction of a line element, of a component, is considered. So in the left diagram, you can see the measurement data from Siemens. Here you can see a heating up process, a global heating up process over the time for a component, and after the exposure, a cooling down procedure at the end of the entire printing process. And the black dots are training data that were used to train the neural network. And in the right diagram, you can see the solution of the found partial differential equation, the deep hidden heat model. The green dots are so-called collocation points. That are solution candidates. Here it is checked if the partial differential equation is satisfied. As can be seen, the found partial differential equation can reproduce the generated sensor data very well, decode the physical laws at the same time, and extrapolate and predict temperature values that lie in the future. The found model represents a kind of black box model, so that's the big disadvantage here. So it's only possible to solve this model again with a deep neural network. But there's also the possibility to formulate a partial differential equation based on physical knowledge. Thus, temperature processes are usually described with the popular heat equation. With the help of another deep neural network, as an initial function, an attempt is made to determine the significant parameters of the heat equation together with the weights and biases of the neural network in such a way that the temperature process during manufacturing can be estimated. The solution of the found model here can approximate it with the physics-informed neural networks as well as with conventional numerical methods. So as you can see in the diagram on the right, this approach works similarly well. The green dots again represent solution candidates, and the entire solution is based on an initial and boundary value problem. So this is necessary to solve a partial differential equation. To the left, the parameter of the partial differential equation were optimized using an optimization procedure and simultaneously solved using the finite difference method. So that one can compare the two solutions and parameters found and validate the physics-informed neural network approach in particular. On this slide, I would like to compare the parameters found and show how the different loss functions converge for the heating process of the nickel-based alloy Inconel 1718. As you can see in the table, the parameters of the continuous heat model are comparable to those of the optimization with the finite difference method. Also in the last row of the table, you can see that the continuous heat model can best reproduce and predict the measured data here. So let us compare the resulting heat models and visualize the results of the different heat models for Inconel 1718. So we can see here how well these physics-informed neural network approaches work. They can definitely compete with the finite difference method. I have also visualized the temperature distribution for 2 points in time for heating up as well as cooling down. Here it can be clarified once again that physics-informed neural networks offer a very good possibility to simulate temperature processes in 3D printing. For the cooling process, the physics-informed neural network approach even provides significantly better results than optimization with the finite difference method. Now let's move on to the second part of my presentation. As mentioned several times, there were strong simplifying assumptions for the models in part 1. In the second part, I will extend the model to 3 dimensions in order to be able to detect errors at an early stage and to react them in good time, and intelligent real-time analysis must be developed. Here you can see how such errors can affect the component quality. I will show you how such deformation can be prevented with the help of the heat model and a prediction of irregularities. I would like to explain the neural network architecture for 3 dimensions. As with the simplified model, we try to train a neural network as universal functions approximator for the temperature fields. Again, these learned functions are derived using automatic differentiation and inserted into the heat transfer equation. It is required to map the temperature distribution within 3D printing as well as possible while satisfying the differential equation and boundary conditions. As announced, real-time analysis must be possible, and for this I have developed the following algorithm. The idea is to stream the data of a printed layer live in real time and train one physics-informed neural network per layer with 500 epochs. At the next layer, all parameters of the previous layer are then passed so that the network of the previous step can be informed by these parameters and trained further. The individual layers should be very similar, so that's the main idea. This way, the neural network can be trained in real time parallel to the printing process. The first results of this procedure I would like to show you here. First, for the inverted pyramid. On the left side, we see the digital heat twin, and on the right side, the temperature data from Siemens. As we can see, the digital heat twin is able to simulate the temperature data. With the help of the temperature gradient on the top surface, important conclusions about the component quality can be drawn. The temperature gradient at points of interest can be used as parameter to reveal irregularities and anomalies that may lead to deformations in the component. High stresses can also be expected at locations with high temperature gradients. There is a correlation between the real deformations of the components and the temperature gradients at the top surfaces. In the left diagram, we can see the temperature gradient along x direction for two components which are printed very well. For component 3, on the other hand, irregularities and anomalies in the temperature gradient can be seen. At this point, it makes no sense to continue the printing process for part 3. Instead, it should be aborted to save materials and costs. Component 4 will also deform considerably during the printing process, so that the printing process for this component should also be stopped after approximately 150 minutes. I would like to demonstrate here again on another component that the method works very well on the one hand, and on the other hand can also be used independently of the component geometry. This is a turbine blade. It is an intelligent generic approach that can analyze temperature processes in real time using learned models. Finally, I would like to give an outlook on how to make the model even more complex and how to include the heat fluid flow. A heat model that takes into account both heat conduction and heat fluid flow can be described using the energy conservation equation and the popular Navier-Stokes equations. T describes the temperature field. Within the flow, there is a certain velocity and a certain pressure at every point. These velocity fields or pressure fields are described with U or V and P respectively. Furthermore, we need an energy source. In our case, this is the laser. And in the literature, it is suggested to define the phase transition from solid to liquid. This is called mushy zone. If we are on the solid area, nothing is flowing, so velocity and pressure fields are zero, and we get the heat equation. So that with the help of these four equations, we can represent both the heat conduction and the heat fluid flow. Radiation here is still neglected in the model. How can we feed this mathematical formulation into a deep neural network and inform it about heat transport and fluid flow in 3D printing? As with the simplified models, we train a neural network, this time with several outputs, as universal functions approximator for the temperature field, velocity field, and pressure field. Again, these learned functions are derived using automatic differentiation and inserted into the energy conservation equation and the popular Navier-Stokes equations. The idea is to learn the velocity fields and pressure fields only from the observations about the temperature profile and the differential equation relations. It is required to map the temperature distribution as well as possible while satisfying the differential equations. Unfortunately, it is not possible on the current data basis to detect melt pools and thus areas with liquid metal, so that other measurement data or numerical simulations must be used. This will be pursued in the future. Let us summarize once again what we have seen. I have shown them a data-driven way to model heating and cooling processes with an additive manufacturing using physics-informed machine learning. I gave you a survey of different physics-informed machine learning approaches applied to 3 different print shops. There was a comparison of different computational approaches with each other, and also evaluation and validation with real experimental measurement data and a conventional numerical solver for partial differential equations. It could be demonstrated that global heating can be learned all through components cooled temporarily, so the method works here stable with noisy data. It could be also shown that the method offers a good viable alternative to numerical methods. So what is the benefit here for 3D printing? With the help of the digital heat twin, the developed algorithm is able to prevent components from overheating, cooling too quickly, and detect irregularities that affect component quality. And the most important point here is an intelligent real-time analysis of the printed parts is possible regardless of the geometry. In the coming months, we will use these methods to demonstrate how 3D printing can be monitored in our living lab. I hope to see you all there soon.